Hello, this is Ibrahim Nassar with Ozone Engineering. In this demo, we will be using the ANSYS EMC Plus tool to simulate the radiated emissions of a PCB placed inside an enclosure and connected to a cable. This demo is part of the ANSYS EMC Plus tutorial examples. Okay, so we will start this demo by opening an EMC Plus design that contains this geometry, which is basically a ground plane here and an enclosure here, which is in this case, it's like a PCB case. And then there's a connector, and through the connector, there's a cable. So to select the top face of this enclosure, and we can right click and select hide. And you see here that cable runs inside the enclosure, and here we're gonna bring the PCB file and place it here. To import the PCB files, we can go to the EMA 3D tab here and click on this button which shows the EDB import. The EDB is kind of the file format that ANSYS is using to translate PCB files into the ANSYS tools. So click on this button. Then if we click here on these three dots, we can navigate to the location of that EDB file, which is here, and we click open. And now it's placed here, so we can move it around. So we want to place it basically here near these conductors. But before that, we want to kind of do some filtering to remove many of the nets that we don't need for this simulation, or just to simplify the model. So to do that, we click here on these three dots as well. And we can select one of the nets and click on the keyboard and Control A to select them all. And we just want to keep two nets, which is this one and the ground one here for this example. And now I want to click on delete to delete all the others. So these are the two nets that we want to keep. Then we click OK. We also going to remove all the components. So clear and hit OK. So now we want to move basically this side. We can use these arrows, or we can go here and put exact dimensions. So if we click on settings, origin, we're going to change the X location to be -80, the Y location to be -30, and the Z location to be 6 millimeters. And we hit OK. Then we click here on the green check mark, and now the file is going to be imported. Now we see that the file is being imported here, and we see now the library of materials is showing up, which shows that we have only copper and FR4 epoxy for the substrate. So if we zoom in here, we should see these conductor or cables or wires connected to these two pads. So here where we're going kind of to assign an excitation later and do the radiation emission analysis. Okay, so now the geometry is imported. Next, we are going to assign the materials. Okay, to assign the materials, we want to assign basically for these conductors and all the other objects. So let's start by assigning the materials for these two wires. To do that, we can go to EMA 3D tab and select materials, and we want to select PEC. And now we have three options for the material selection. So we have 3D objects or surfaces and lines. So here we want to select these two lines. We want to click here. Then we want to select the first line, and we gonna also click on the second one. So now both are selected, and we click on the green check mark. And we can verify now that that these two wires are assigned as PEC by going here to this tree and click on PEC. All right, this PEC, and you see now they got highlighted. Now we want to assign the material for the enclosure and the other objects. To do that, we can go to Materials and click Isotropic. And we can define a material or use the material library to select one of these materials. But here let's define one to be aluminum, Al. And we click on General. We can give it a color. So let's give it like a gray. And we want to change the conductivity to be 1.9 E7. Okay. And now we want to basically select these objects. So we can go to this, select bodies. And here we can select it from the project tree here. So let's expand the EMC enclosure. And we want to assign it to the enclosure. We want to click also on the cable connector. And we want to click on the fasteners. And we want to also select the ground plane and the wall connector. And now you see like they got selected, and we click on the green check mark. Similarly, we can go here, select this material from the libraries to see what is being selected. So now we completed the material assignment. Okay, so now we want to assign the shield to the conductor that runs between the connector all the way to this electric wall, but not inside. To do that, we go to the MHARNESS tab and we click on cabling and we select the shield. Okay, we go to the line selection mode and we want to select where we want to apply the shield, which will be to this wire from the connector all the way to the electric wall, but not inside the connector. And next, we want to define where this will be terminated. So to do that, we go to the point, select a point, and we want to select this point. So you see it highlighted, and this point, the other end. So now the tool understands that this shield will be just between those 2 points. Next, we want to set the properties and the size of the shield. To do that, we click on Library, and we can go to the library here of all the definitions. And when I select TSP, Twisted Shear Shield Pair, and when I select 26 gauge TSP, and we hit OK. And now we just click on the green check mark. Okay, now we want to define the and now we want to define the conductor for the inside that shield. To do that, we can right click on the shield here under the harness tab and click on add and select conductor. So where we want this conductor to be, we want it to be here, right? And we want it also to go inside here and then go to the right side. And we want to select the termination, the point here, to select the termination. So this is the first termination. We zoom out and select the other point. And these is the other termination. Now to set its properties, same thing, we want to click on library and go to library here. Click general, and we want to select a bare wire, and we want to select the 26 gauge wire. Hit OK. And we want to modify here the jacket size to be, instead of 0.254, to be 0.0254. Other things we want to do here is the termination. So we need to be here 50 ohm, but here we want it to be 0 ohm. So by default, both will be 0 ohm. So to make that adjustment, we click on termination and click here on terminations. And now we see the 2 points here. Once I click on it, you see it get highlighted with pink. So this one we need it to be 50 ohm. And this one stay as 0 ohm. Then we click X and we click on the green check mark. So now we define the first conductor, right? But the cable, as you know, it should have two conductors. So one will be going to the right side and one will be go to the left side. So to do that, we can just select the same conductor that we just defined, as it would have the same properties, and right click and say copy, and it's going to be copied. Now we can edit it, and we click on edit. And the first thing we need to do is to unselect that section, and we want to select this section now. And now we want to remove that termination. So we're going to click here and select a point, and we click here. So now there's nothing going to that side, and this would be my termination. And similarly, want to select the other end, which should already be selected. Now we can verify by clicking here on terminations. So this one, which is the other one, so this one is 50 as you see, and the other termination is 0 ohm. Now we click the green check mark. So now we have the cable fully defined, and to do some verification here, we can go to the MHARNESS tab and go to cabling and click this button to inspect the cross section. So if we put the marker here at this cable, so you see now how it is defined, the cable outside the enclosure, or the one that connects between the electric wall and the connector. So you see we have a 2-wire cable and it has a shield, but once we get inside the connector, what happens is we have the same thing, but without a shield, and then as it gets splitted here, so it can become as a one conductor here, 1 wire, and the other side also same thing, 1 wire. Then it connects to the PEC conductor that we defined for the 2 wires that connects to directly to the PCB. Okay, so now we want to define the excitation, and we want the excitation to be defined here on these wires. Okay. So let's rotate this model. We want to define it on these wires, which basically connects to these pads. So how do we want to define it? We want to define to this wire to be PEC, this wire to be PEC, and here's the current source. To do that, the easiest way is that we select this wire, and we right-click and we say assign line material to be PEC. Similarly, we can select this wire and right-click and assign line material and select PEC. Or we can do this from here by expanding the free lines and select which one of those and thus define the material. Now we want to define the current source here. To do that, we can go to the EMA 3D tab and go to excitation and select current source here. And we need to select the geometry for the current source. We want to go to the line selection mode, and we want to select that section. And here you can select whether you want current type electric or magnetic, or the X direction, which the current direction. So I want to keep it here to be the X, and we're gonna now next click on the green check mark. Okay. And as you see, the direction is going from the right to the left, and that's how we want it. Okay. Okay, so now after we define the current source, we need to define the signal on that current source. To do that, we go to the same thing, EMA 3D tab, and want to select a rectangular signal. And here we can do modification to that and define the signal that we want. But here let's define a 0.75 duty cycle, a frequency of 20 megahertz to 20 E6, and the rise and fall time to 10 nanoseconds, so it will be 10 E minus 8. Oh, why it's changed. 10 nanoseconds E minus 9, sorry. And here similarly, 10 E minus 9. for the rise and fall time. We can give it a different name, or we can keep it, and we just click X. So now if we scroll down, we see that the signal got defined here. Now we need to attach that signal to the current source we want. So to do that, we click on the signal and drag it and drop it on top of the current source. And now they got attached to each other. Okay, now we want to define the solution domain. To do that, we click on domain here, and we can change it manually or define it here. First, want to change the time. Let's set the stability margin to 20%. And we want to change this to an E-7. And let's now minimize that and want to change now the lattice, the minimum, maximum, and step size. The first thing we want to adjust is the step size. So let's change that to be 1.5875. And let's copy that number and paste it here. Paste it here as well. And now we want to change the minimum to be minus 180.975. Minimum Y to be minus 147.6375. Minimum Z to be minus 12.7. Maximum to be 196.85. 533.4. And maximum Z 109.5375. And now we can click on the green check mark. And now this is the solution domain. Okay, so now when we define the solution domain, which encloses the entire geometry. And as you remember, the domain has a step size of 1.587, right? But we need a smaller step size for the area or the volume that encloses the PCB. So to do that, what we can do is to add another domain that encloses the PCB, and that is possible here by going to the EMA 3D tab and select the variable grid. And similarly, we can place it wherever we want manually, or we can define it here. So let's define the step size here to be 0.24, to be much smaller than the step size for the larger domain that encloses everything. So we want to make the X step size to be 0.24, and 0.24 for the Y, and 0.36 for the Z to have a finer meshing for the PCB. And we also want to change the location of it, so the minimum to be minus 83.04, minus 36.48, 5.04, and for the maximum X, minus 21.12, 30, and for the Z, 7.92. And we're going to click the green check mark. So now we see, if we zoom in here, that there's another domain defined for called the variable grid 1, defined around the PCB. Now, since we have two different domains with two different step sizes, this can create an issue for the MHARNESS. The reason for that is, for this domain, the smaller step size will need to be gradually changing as you exit from this domain to the larger domain. So the step size around the MHARNESS will not be uniform, and that can create an issue with solving the MHARNESS. To do that, we want to define another variable grid to ensure that we have a constant step size along the route of the MHARNESS. To do that, same thing, we define another variable grid mesh. And we want to give these dimensions. So let's change the step size to be 0.5, 0.5, and 0.5. And for the minimum to enclose the MHARNESS would be 24, 69, 32. And the maximum is 54, 457, and 41. And we're going to click the green check mark. So now we see this domain encloses the MHARNESS to ensure the constant step size. So after the domains are defined, we need to define probes to be able to measure the fields. To do that, we go to the EMA 3D tab, and we want to define multiple probes. So the first probe we want to define is a point probe. So if we rotate the model, we see like there's a point floating, so we can just click on it. And now you see there's a point field probe defined here and listed under probes. We also want to define a 3D probe. So we go again to fields and we select 3D probe. And similarly, we can manually place it and define that size, or we can do it from here. So let's go expand bonds, minimum and maximum. And we want to define this to be 22.225 and minus 117.475, 52.387, 187.325, 476.25, 55.5625. And when I expand the time, start, step, and end, we don't want it to be matching the domain, so we want to change that to be 4e minus 10 seconds, and end 1e minus 8. And for the step, we want to change this to false and define it manually to be 2e minus 10. And then we click on the green check mark. And so this is the 3D probe that is defined. Next, let's just confirm the simulation settings. So we can go click here on settings. If you have GPU, make sure that this is checked. And significant figures displayed, yeah, let's make this 7. And that's it. Click Apply Settings. Now we can start meshing and simulating the model. To do that, we click here on Mesh to mesh the model. So now the mesh is created, and we can zoom in and rotate the model to inspect it. As you see here, after the mesh is created, we can click on Start to start the simulation. It will do first validation check. And now we can click Run. And this simulation will take a while depending on the computer resources that you have. So now after the simulation is done, we can look at the results. So we can go to the field prop we defined and compute the field statistics. And we point to the current source that we used. And we click OK. And the field statistics get calculated. And now we see under visualization the results. So we can right click on field statistics now and click on show. And this is the field statistic data. We can right click and configure this plot and chart. We can change that from, for example, to dB. And you can make different changes. We can also plot the fields along the bulk data probe, which is the 3D probe that we defined. So we can do that by right-click on the bulk data probe and select Visualize 3D. And now, because we define many time steps, we can select which time step we want to plot the fields at. So for example, let's select this point and click on Visualize Results. And as well, you can save it as a JPEG. So let's click on Visualize Results. And if you don't see it, you need to select this option here for contours. And now we see the field plot. You can plot the electric field in the X, the Y, the Z, or the magnitude, and you can modify the scale. You can as well plot it at different time steps, say 10. And then you can click here to select which one you want. And that's all for this demo, and thank you for watching.